Hello there, Mr. Sutton here with the AB Calculus 513 homework solutions on average value.
For this calculator-based problem, we want the average value of tan of x squared over 9 on the interval from 1.25 to 2. So we'll just use our average value formula for this. That's 1 over b minus a times the integral from a to b of the original function. So in this case, we're going to have 1 over 2 minus 1.25 times the integral from 1.25 to 2 of, well, we're just going to put this whole original function in here, tan of x squared over 9 dx. And now we'll just do this on Desmos because it is a calculator problem. So just to make my life a little bit easier, let me just create a name for the original function. We'll call it f of x, and we'll just make it this tan of, let's see, parentheses, x squared over 9. Close the parentheses. Now I'll do my average value. 1 divided by 2 minus 1.25 times the integral int from 1.25 to 2. And I can just write f of x dx in here now. And that comes out to about 0.099, so I guess 0.310 if we round it to 3 decimals, giving us choice C.
For this no calculator problem, we're trying to find the average value of 1 over x on the interval from 4 to 6. Using our average value formula, we're going to have 1 over b minus a, so 1 over 6 minus 4, times the integral from 4 to 6 of this f of x function up here, 1 over x dx. So now let me go ahead and take my antiderivative. So I'm going to have 1 over 2 times, well, the antiderivative of 1 over x is ln of absolute value of x. And it's up to you whether you wanted the absolute value here. You actually technically only need it if you're going to be plugging negatives in, and 4 and 6 are not negative, so you could have left it out here or left it in either way. So plugging in 6 and 4, we've got 1/2 times ln of 6 minus ln of 4. And let's see here, is that any of my answer choices yet? It is not. So let's keep going. So one thing they often have us do with these ln's is combine them using log rules. If I'm subtracting the same logs, then I can move them together by dividing the things inside. So I can write this as 1/2 of ln of 6 over 4, which I could reduce to 1/2 ln of 3 over 2, which is finally one of the answer choices, choice C. For number 3, on a closed interval from 2 to 4, which of the following could be the graph of f such that the average value of f equals 1? That's what this is saying here, right? Average value. So if you recognize this is average value being 1, then we just have to see a graph that has that property. Okay, let's go through each of them. So for A, the average value being 1, not so much. So we are passing through 1, but we're above 1 a whole lot more of the time than we're below 1. So A is going to give us a value that's a little bit too high for the average value. And we have that same issue with actually D and E. If you look at D, we're only 1 this one time, and the rest of the time we're well above 1. And E, we're never even 1. This is going to have an average value of 2. It's just a horizontal line through 2. So A, D, and E, the numbers are going to be too high. That leaves B and C. Now for B, it's a little bit more evened out, but we're still below 1, literally twice as long as we're above 1 here. So B is actually going to give us an average that's too low. It's only choice C then that makes sense. And if you look at this, we're above and below 1 for about the same amount of time. So choice C then is our best answer. On this no calculator problem, we're given that the height of an object suspended from a spring is this 16 plus 7 cosine pi t over 4 function. Based off of that, we want the average height of the object from time 0 to time 2. Okay, so we're going to need to use our average value formula, 1 over b minus a times the integral from a to b of whatever you're averaging. So in this case, we're going to have 1 over 2 minus 0, that's b minus a there, times the integral from 0 to 2 of this h function up here. So let's go ahead and take that antiderivative. So we're going to have 1/2 times, and now for the antiderivative, going from left to right, we've got 16t. And then this next one's going to be a little bit tricky. The antiderivative of cosine is sine, but we also have to divide by the linear tail here because we've got a linear function inside. So we're dividing by pi over 4, but that means we're multiplying by 4 over pi. So this is going to be 28 over pi sine of pi t over 4. And that's all going from 0 to 2. All right, well, at this point, let's go ahead and plug in 2 and 0. We'll just leave the 1/2 out there. So we've got all this stuff with 2 plugged in minus all of this stuff with 0 plugged in. So as we're going through here, this looks kind of nasty. The good news is that 16 times 0 is 0. This is essentially sine of 0 over here, which comes out to 0. So this whole second bracket of stuff that came from 0 is all just going to come out to 0. So really, it's just down to this first bracket, which gives us a 32. And over here, let's see, this is going to be sine of essentially pi over 2. Sine of pi over 2 is just 1. So this just ends up being plus 28 over pi. And that isn't quite one of the answer choices yet, so let's go through and multiply by 1/2. That'll be 16 plus, if we reduce by 2 here, this is going to be 14 over pi. So that gives us answer choice D.
On this calculator-based problem, we're told that the temperature in degrees Fahrenheit of a coffee cup 10 minutes after being poured is given by this f of t function, which is this weird exponential sort of function, decaying exponential function. To the nearest degree, we want the average temperature of the coffee from time 0 to 10 minutes. So we can just use our average value formula on this. That's 1 over b minus a, so in this case 1 over 10 minus 0, times the integral from a to b, so integral from 0 to 10, of whatever it is we're trying to average, which in this case is just this f of t function. We just want to average the temperature. And I'm just going to plug all of this into Desmos. So go into Desmos. Let me first write my f of t function. So that was 72 plus 118 times e, exponent negative 0.093t. And now let me just do 1 over, I can just do 1 over 10, integral from 0 to 10, and then we'll put in f of t dt. And if we round that to the nearest degree, that's going to be 149 degrees, and that is in Fahrenheit. So that's going to give us answer choice D.
On this problem, we're given this piecewise function, and we want the average value of this function on the interval from 0 to 5, which, of course, includes the border value that splits up these rules. So we're going to essentially set up our average value formula. We've got 1 over b minus a, which in this case is 5 minus 0, and we're doing the integral from 0 to 3 of this first rule here, which I'm converting that into a 1/2 power just to make it easier to take the antiderivative in a minute. And then I have to also add in the second integral representing this second rule, so I'm going to have the integral from 3 to 5 of 5 minus x dx. All right, let me go ahead and do the rest of this now. So this is going to be 1/5 out in front, and I'm going to take the antiderivatives of these now. So this here is just the reverse power rule. This bumps up to a 3/2, and we're multiplying by the reciprocal of that, 2/3. So this is going to be 2/3 x plus 1 to the 3/2, and that's going to be from 0 to 3 that we're evaluating that one. This next one, going from left to right, we've got 5x minus 1/2 x squared, going from 3 to 5 on that one. And here's where it gets really fun. So I've got my 1/5 still, and inside a big parentheses now, I'm just going to keep this 2/3 outside, and I'm going to do this stuff with 3 and 0 plugged in inside. So I've got 2/3, and then this stuff with 3 plugged in, and I'm going to rewrite this as the square root of x plus 1 cubed. So I've got a 3 plugged into that. And now I'm going to be subtracting essentially this with 0 plugged in. And now I have all this other stuff over here. So I have 5x minus 1/2 x squared with 5 plugged in, and that's getting added. And then we're subtracting all of this stuff over here with 3 plugged in. Now, it's important to note that this is a free response problem, and on the AP exam, as long as everything is a constant, you could actually leave this unsimplified unless you needed it for some other purpose. But for this problem, you could actually stop here and just be done. But I'm going to go ahead and keep simplifying it just for the sake of simplifying. Feel free to move on if you're done watching, but let's keep simplifying. So in here now, we've got, let's see, this is the square root of 4, which is 2. Cubing that gives me an 8. And this is going to be a 1 when the dust settles over here. So I've got my 1/5, my 2/3, and now in parentheses next to that, I've got an 8 minus 1. And then let's evaluate the stuff over here. This is 25 minus 25 over 2. So 50 over 2 minus 25 over 2 is 25 over 2. And for this stuff over here, I've got 15 minus 9 over 2. Well, that's really like 30 over 2 minus 9 over 2. That's 21 over 2 that we're subtracting from all there. What else can I do now? Well, 8 minus 1 is 7, times 2 is 14, so I've got a 1/5 times, this is going to be 14 over 3, and then over here I've got 25 minus 21 over 2, that's 4 over 2, which is just 2. Let's keep going because we're simplifying for the fun of it. This is really 14/3 plus 6/3, that's 20/3, and if I do 20/3 divided by 5, that's going to be 4/3 when all is said and done. Or you could have just stopped up here.
For this calculator-based free response problem, we have concert tickets going on sale at time 0 at noon and selling out within 9 hours. And they've got this table here telling us how many people are waiting in line at each time. And that's a twice differentiable function L they're telling us. Now, values of L of t, let's see, they gave that in the table. For part B, they want to know a trapezoidal sum with 3 subintervals that estimates the average number of people that are waiting in line during the first 4 hours that the tickets are on sale. So using our average value formula, we have 1 over b minus a, and since our interval is from 0 to 4, that's going to be 1 over 4 minus 0, times the interval from a to b, so in this case from 0 to 4, of the function that we are trying to get the average for. Well, we want to average the waiting in line function here, so L of t dt. This is the general setup. We're going to have to put a few specifics in here, though. Now, since I am approximating, I'm going to write approximately equals, and I can simplify this to 1 over 4. And my integral now, I'm going to replace this with my trapezoidal sum. So the first interval, we're going from 0 to 1. So we've got 120 plus 156 over 2 times the interval length of 1. That's my first trapezoid area right there. For my next trapezoid, I'm going from 1 to 3. So 156 plus 176 over 2 times the interval length of 2, 3 minus 1. And then my last trapezoid from 3 to 4, we've got 176 plus 126 over 2 times interval length of 1. And if I were to put units on this, it would be in units of people here because that was the function we're averaging. I could actually just be done with the problem if I put people and stopped here. But if you wanted to simplify it, you could use the calculator to do that. I don't recommend it on the actual AP exam, but let me go to Desmos and just see what the actual average is because I'm curious. So we've got 1 over 4, and then parentheses, and then fraction, 120 plus 156 over 2, and I don't need to bother writing times 1 for that one. And then we've got fraction again, 156 plus 176 over 2 times 2 plus fraction 176 plus 126 over 2. Don't need to worry about the 1. Close this out. And that's about 155.25. And we're approximating it here. So, we already wrote the squiggly equals. That's in people. That's the average number of people waiting in line at any given time. For this next part of the problem, we're told that the rate at which tickets are sold from time 0 to 9 is modeled by this R of t weird linear product exponential function. Based on this, we want to know how many tickets were sold by 3 p.m. to the nearest whole number. So we've got the rate of change to figure out the total number of tickets kind of accumulated over this time from 0 to 3. We just need the integral of this rate of change, this r of t, from 0 to 3. So integral 0 to 3 of, I could even just, if I wanted to, write r of t in there. There we go. That's a little cleaner looking. I mean, they did define it, so we can use the name. Now, I'm actually going to have to do this on Desmos, so let me go there, and let me put in my r of t function. So r of t equals 550 t e exponent negative t over 2. There we go. That looks like what I was given in the problem. And I now need the integral of this thing from 0 to 3. So int 0 to 3 r of t dt gives us, they wanted the nearest whole number, so 973 tickets sold.
For number 8, we're going to be using this table here. As a pot of tea cools, temperature of the tea is modeled by a function from 0 to 10, and we've got some selective values of that h function given in this table, and this is in degrees Celsius that we're measuring this in. And we want to use the data in the table to approximate the rate at which the temperature of tea is changing at time 3.5. Okay, so there's no way we're going to be able to find the exact rate, but we can approximate it by finding the average rate of change. So for that, we have 52 minus 60 over 5 minus 2. We're just going to use the values that are right around this 3.5 that we're looking for. So we're doing AROC, and I'm going to first show that I'm doing h of 5 minus h of 2 over 5 minus 2, just so that they can see where those top values are actually coming from. So again, that's 52 minus 60. That'll be 3 down there. And I could actually just leave it like this and stick, let's see, this would be degrees Celsius per minute on the end, or you can change it to negative 8 over 3 degrees Celsius per minute, either way. For this part of the problem, using correct units, explain the meaning of 1/10 integral 0 to 10 of h of t dt in the context of the problem. And then they're going to have us do a trapezoidal sum, but let's tackle this first part first. So what does this stuff mean? Well, h of t, they told us, that's the temperature of the tea that's cooling. So if you're doing 1 over 10 times the integral from 0 to 10 of h of t, this is going to give you the average value of the temperature. So this is the average temperature of the tea, but there's a few other things you need in your explanation. They said using correct units. So you need to specify the units for this average. Now the units of an average are always going to be the same as the units for the original quantity. So this is going to be in degrees Celsius. And there is one other piece we need here. Whenever you're doing something within the context of a problem, you need to give a time period for these things. So this is the average temperature over the time period from 0 to 10 minutes. If you didn't specify 0 to 10 minutes, you probably would not get that point. All right, so now that we've done that, use a trapezoidal sum with 4 subintervals indicated by the table to estimate this average value. So we've got our average value there, and I'm going to write approximately equals, and now the rest of this. And you need this approximately equals because it is an estimate. You're not actually giving the true average value of the t, you're just estimating it based off of this table, because we don't know what's going on in between these table values. So we've got the 1/10 that's part of our average value, and now we're going to do the actual integral part. So they said using trapezoids. So we've got an integral from 0 to 2. That's a height of 2. So we've got 66 plus 60 over 2 times this height of 2. Next, we've got 60 plus 52 over 2 times a height of 3 to go from 2 to 5. And next, 52 plus 44 over 2 times a height of 4. And finally, 44 plus 43 over 2 times a height of 1. And as long as you put units on this, right, degrees Celsius here, you're actually done with the problem. But if you wanted, this was a calculator problem, so you could have actually gone through and calculated the final number for this, which I'll do now. So plug in all that craziness in my calculator, and by the way, I used alpha, y equals, and n over d to get these fancy fractions. That comes out to, let's see, I don't really want a fraction there. Let me math decimal that thing to get 52.95. And really, they don't care if you simplify it as long as you write degrees Celsius on your final answer here. For part C, they want us to evaluate the integral from 0 to 10 of h prime of t dt, and then using correct units explain what it means. So when we're doing this, we're basically using our fundamental theorem of calculus. So we have the antiderivative of h prime, which is just h. So we've got h of 10 minus h of 0, again using our fundamental theorem. Now h of 10, they gave us that in the table. That's just 43. H of 0 up here is 66, so this is just 43 minus 66, which comes out to, let's see, this will be negative 23, and this is going to be degrees Celsius. H prime was the rate at which the temperature was changing, so if you integrate that, you get the total change in temperature. So just to write out what this actually means, this is the total change in degrees Celsius of the T's temperature from 0 to 10 minutes. So you had to get the total change in there, you had to put your units, degrees Celsius, and again you had to specify that this was from 0 to 10 minutes, because the total change is going to change depending on your time interval. And then I added this little extra bit about the T cooling by 23 degrees Celsius over the time interval. This last bit probably wasn't necessary, but just to confirm the kill, so to speak. But definitely you need the 0 to 10 minutes there. For part D of this question, at time 10, biscuits with a temperature of 100 degrees Celsius were removed from the oven. Temperature of the biscuits at time t is modeled by differentiable function b, which they're not going to tell us, but what they will tell us that b prime of t is this crazy exponential function. Using these models, at time 10, how much cooler are the biscuits than the tea? So they're telling us the biscuits are cooler than the tea, and they're essentially asking us what is the difference between tea temperature at time 10 and biscuit temperature at time 10. In other words, what is h of 10 minus b of 10? So we know what h of 10 is. That's just 43. They gave it to us in the table. For b of 10, however, we're going to need to set up a little fundamental theorem kind of expression to represent that. So we know the initial temperature of biscuits. It's 100. And this is at time 0. We also know the rate of change of the temperature of the biscuits. It's this function here. So since we have an initial value and the rate of change for the function whose value we want to find, we can set up the following expression. So we can say this is h of 10 minus, and then in a parentheses, b of 0 plus the integral from 0 to 10 of b prime of t dt. Now you could write this exponential again, but honestly they defined it for you in the problem. So just to save time, you really should just write b prime here and let the calculator do the work on this. So alright, let's flesh this out a little bit more, and then it's pretty soon going to be time for the calculator. So h of 10 again, that was 43. b of 0 was 100. We've plugged in all the easy stuff. Let's use the calculator for this last piece. To make my life a little bit easier on this, I'm actually going to enter this function here in for my y1 in the calculator. I'm going to be plugging this into an integral anyway, as you see down here, but it'll be a little bit easier to plug in if I'm just using y1 instead of all this stuff. Alright, let's quit out to the main screen. And I'm really just going to do all this at once. So we've got 43, here we go. Oops. There we go, calculator was misbehaving. Minus, we've got parentheses 100 plus integral, so we need math 9. And our integral is going from 0 up to 10. And I already entered this function under y1, so I'll just do alpha and then trace to bring up y1 there. And we want dx. No need to close the parentheses, let's just press enter. And that all comes out to about 8.817 if I round off to the nearest 3 decimals. And that's going to be in degrees Celsius. Now, you haven't actually answered the question yet. You need to actually state that the biscuits are about 8.817 degrees Celsius cooler than the tea at 10 minutes. You You know what this means. They probably know what this means, but how do they know that you know what this means? So when in doubt, spell it out.
For this calculator-based free response problem, we have the temperature of water in a tub at time t modeled by a strictly increasing twice differentiable function w, and Wt is measured in degrees Fahrenheit, T is measured in minutes. At time zero, temperature is 55 degrees Fahrenheit. Water is heated for 30 minutes, beginning at time zero, and some values of Wt at selected times are given in the table here. So they didn't give us the whole picture, but they gave us a few snapshots. So based off of this, the first thing they want us to do is use the data in the table to estimate W prime of 12, show the computations, and using correct units, interpret the meaning in context. All right, well, let's get W prime of 12 estimated first. Since we're looking for the rate of change of W and we only have this table to go on, we're going to average this by finding, estimate this by finding the average rate of change of W over an interval that includes 12. Now, the smallest interval including 12 is the interval from 9 to 15. So I'm going to find the AROC of W from 9 to 15. That's going to be F of, or actually in this case, W of 15 minus W of 9 over 15 minus 9. So specifically, that's going to be 67.9 minus 61.8 over, I guess I could make that 6. And notice I wrote approximately equals here, so I'm being a truth in advertising here. Now, you could leave this the way it is and put units on it. You don't have to simplify it, but if you do simplify it, let's see what we get. So go into Desmos and plug in this in. We've got fractions 67.9 minus 61.8 over 6, and that rounds off to about 1.017. Now, what are the units going to be on this? Since we're taking a W thing up here and dividing by time, it's going to be degrees Fahrenheit over minutes for our units. So 1.017 degrees Fahrenheit per minute. Now, what does this actually mean in context? So for the context, we always need three things. We need to know what this actually means numerically. We need the units, and we also need the time linked to it as well. So W prime of 12, we're saying at time 12 minutes, the water temperature, that's the thing, is increasing or rising by 1.017 degrees Fahrenheit per minute. So we've got the time, 12 minutes, what it is, temperature rising, and there's our units.
For part B, using the data, they want us to evaluate integral from 0 to 20 of W prime of t, and then interpret it. So we just need an antiderivative here. The antiderivative of W prime is just W. So we're just using our fundamental theorem. We're doing W of 20 minus W of 0. Now the good news is we have table values for those values of W. So this is just 71 minus 55. And you actually don't have to evaluate what that comes out to, but we will. It comes out to 16.0 degrees Fahrenheit. So now here's the other part of the problem where we have to interpret what this means. Since we took an integral of a rate of change, we're getting the total change in whatever was changing. Temperature was changing. So this expression is the total change in degrees Fahrenheit. We'll just throw the units in there again to be on the safe side, of the temperature over the interval 0 to 20 minutes. Again, we have to have this time in here. Otherwise, who knows what this change is really happening over. And then, just for good measure, we'll say the temp increases 16 degrees Fahrenheit.
For part C of this problem, we're told that from time 0 to 20, the average temperature of the water in the tub is 1/20th integral 0 to 20 of Wt dt. That's not really news. We could have figured that out on our own, but they're kind of giving that to us. They want us to use a left Riemann sum with 4 subintervals with the data in the table to approximate that. And then they want to know if that's going to over or underestimate the average temperature of the water, the true average temperature of the water over these 20 minutes, with reasoning. Okay, so let's approximate this average, left Riemann sum. So that means that I need to always take the left output value for each of my rectangles. So I'm going to have a base of 4 for my first rectangle, times the left rectangle height here, so 55. So 4 times 55 is going to be our first rectangle. And I'm going to write average temperature is approximately equal to all of this. And don't forget about the 1 over 20 that should go out in front of all of this, right? Because we need that to get the average and not just like the total accumulated temperature over the time. All right, so for my next rectangle, from 4 to 9, that's a distance of 5 times the left part of it of 57.1. Next, from 9 to 15, we've got a distance of 6, base of 6, times the left height of 61.8. And then finally, for our last interval, this is a base of 5 times the left height of 67.9. Now, you don't have to simplify this. You could leave this the way it is and just stick the units on there. Since this is an average, it is going to be degrees Fahrenheit. However, if you wanted to figure out what that actually is, we can go to Desmos and plug it all in. So we've got 1 divided by 20 times parentheses 4 times 55.0 plus 5 times 57.1 plus 6 times 61.8 plus 5 times 67.9. Close the parentheses if you want. And that's about 60.79. And again, that's degrees Fahrenheit. Now, is this an over or an underestimate? To figure that out with Riemann sum approximations, we need to look to see if the thing that we're approximating is an increasing or a decreasing function. Now, they told us here temperature of water, W of T, is a strictly increasing differentiable function. So it's increasing along the whole interval that we're trying to average here. Since W of T is strictly increasing on the interval from 0 to 20, it's important to specify 0 to 20 because that's the interval we care about. That tells us that LRAM is going to under-approximate. LRAM always underestimates when you have an increasing function. RRAM would have overestimated. So there we are. For part D of this problem, this is kind of the epilogue to the first 3 parts because this table stops at 20, but you might wonder what happens after 20. Well, they're going to tell you. For times 20 to 25, the function w that models the water temperature has a first derivative given by this w prime of t, this weird square root cosine sort of function. Based on that model, they want the temperature of the water at time 25. So they didn't tell us what w of t itself was, but they gave us w prime, and they gave us, we actually know a starting value. We know at time 20, we have the exact temperature of 71.0. So we can use fundamental theorem of calculus to go the rest of the distance. So we're going to do our initial value plus the integral from 20 to 25 of this w prime. So here's what the setup looks like. We have w of 25 equals w of 20 plus integral from 20 to 25 of, and I'm just going to write w prime of t. I don't need to copy that down here. Now I actually have to enter this in my calculator, and here's what I'm actually going to enter into my calculator. So my w of 20, we know that that's 71.0, and this integral I'm going to enter kind of as is. I'm going to tweak it a little bit though. So going back to my calculator, let me clear out what's already in there, and let me write in the w prime function. Now when I do this, I can't actually write w prime because my calculator doesn't know what w is, so putting a prime on it is going to confuse it. I'm just going to call it g. So g of t equals 0.4 square root of t, and then get out of there, arrow out of that square root, and then we've got cosine of 0.06 t, and that is my that's my function. So let me go down here now and just do 71 plus integral int from 20 to 25, and now I can just put in g of t dt, and that comes out to 73.043. So that's going to be our Fahrenheit at time 25.